Hello, it's a great pleasure to be with you today. I'm going to speak about calibrating real-world evidence against randomized controlled trial evidence. What's the rationale and what are the methodologic challenges and hiccups when we do these calibration exercises? My name is Sebastian Schneeweiss and I'm a professor of medicine at Harvard Medical School. Here are my disclosures. You can pause the video stream in order to read this. Now, what do we wish to learn from replicating randomized controlled trials with real-world evidence? It is really addressing the number one credibility issue of real-world evidence, the elephant in the room. Can real-world evidence estimate causal treatment effects in a given study? Can we come to the true underlying treatment effect that is in the nature, and can we estimate this reliably? For that, the question then is, can we calibrate real-world evidence findings against the true causal treatment effect? Well, for that, we need to know the truth. And that is really just tough. Unless we are the one, we will not know what the truth is. So what is the next best thing? Relying on expert opinion? Probably not. We tried this before. Statistical simulation studies? Probably not. They are very useful in understanding how specific statistical tools work, but they are not giving us the answer here. Comparing real-world evidence findings against RCT findings. Well, based on the assumption that a well-planned and well-executed RCT is accepted as having a causal interpretation, this is worth trying. This is the next best thing to a causal finding, causal treatment effect finding. So why not do that? Or if you do have any better idea, please do share that with us in the community. We need some sort of gold standard to calibrate against, otherwise the whole exercise is meaningless. Why is this so important? Well, if real-world evidence cannot estimate causal treatment effect, what really is the point of that? In medicine, as we use medical products in treating our patients, we need to know that it really works in these patients rather than being a spurious association where we don't know, is it the disease that is leading to this outcome or is it a treatment that is leading to this outcome? So causality is critically important. Now, when I listen to the different communities out there, the real-world evidence proponents, they seem to say, I've heard these comments, real-world evidence studies answer different questions than RCTs, and therefore you should never expect the same findings. I heard even more extreme comments like, you should not compare, it may backfire, Sebastian, don't do this. And to me that translates, we can never really test the validity of real-world evidence because we don't have an agreeable gold standard to test against. That is quite dissatisfying and reminded me of Karl Popper noting that, if a hypothesis evades testability, it is not a viable hypothesis. So can we really hide behind this argument? And of course, what I hear from the RCT proponents is that real-world evidence studies have never been able to convincingly demonstrate that they have causal conclusions like RCTs have. And to me, that translates, well, the bar is set high and we're open to listening, but doubt that real-world evidence will ever be trusted. So we have to get those two communities together and we have to do better in being responsive to these needs in order to demonstrate that real-world evidence can lead to causal conclusions. What we don't mean is equally important. We don't mean to imply that all real-world evidence studies need to calibrate against an RCT. That would totally defeat the purpose, of course. Real-world evidence is there to complement RCTs because we may expand to other study populations. We may want to study other treatment patterns. We may be interested in slightly different endpoints and things like that. It is the purpose of real-world evidence to go beyond the RCTs. But we need to also find examples where we can calibrate, and we need to learn from that. When does it work? When does it not work? What is going wrong in studies and what is going well in real-world evidence studies in order to come closer to a causal interpretation. Now, some considerations here for RCT emulations. The question is whether the real-world evidence finding is equal to the RCT finding. Now, if we do that and we actually, get the same finding, the real-world evidence finding is equal or close enough to the RCT finding, well, first, we go out to celebrate. Secondly, we wake up the next morning and we had doubts. Were we just lucky? If we would repeat this study, the real evidence study, do we still get the same finding? And to some extent, the repeat projects by Shirley Wang and other projects are getting at that, how reproducible is our real-world evidence studies, even in best circumstances. And if we do get the same findings, how many times should we successfully do that in order to generalize our conclusion that, yes, real-world evidence can actually emulate RCTs and come to the same conclusion? And can we predict ongoing RCTs? That's the ultimate test. Now, in the situation where we don't find the same relationship, the same finding, what then? There are a bunch of questions that come up. One is, well, what about our gold standard? How variable is our gold standard? Is the one RCT finding that we have really the true treatment effect? And if we would repeat that, what is the variability between multiple RCTs? Are they all getting the same finding, or is there variation around that? And how much is that variation? Is it just as much as the variation between RCT and real-world evidence? So that is one concern. The second concern is this just an emulation failure? Did we not mimic the RCT? Did we study something else? We had a causal treatment effect, but it's a different effect. It is a different population, different treatment pattern, different outcome measurement, and things like that. So these two don't lend themselves to be compared. And thirdly, well, it is bias operating. Bias is the reason that we have a different finding, and that can be confounding, the differential surveillance biases, time-related biases, and so on. And this is what we're really after when we do these calibration exercises, right? What are the biases operating, and how can we overcome these biases operating? Ideally, we would not have any difficulty with the emulation, and ideally, we have a clearly agreeable gold standard. Well, thinking about the emulation, I'm not going through all these examples here. There are plenty of what we have learned from our RC duplicate project, but here just a couple of nuggets in the exclusion criteria bucket in the red text here. One of exclusions in the randomized trial is not that infrequent, actually. The patients are likely to die within the next 6 months, and therefore we will exclude those patients. And I'm scratching my head and thinking, but how do you do this in a randomized trial? How does a investigator in a randomized trial running one of the sites in a large multi-site randomized controlled trial, how would that investigator decide whether that patient has less than 6 months to live, or maybe can live till month 7, 8, 9, 10, right? And of course, how do you operationalize that then in the real-world evidence study? Another exclusion criteria is range, parameter range, like an age range, for example. An age we can measure very well in our data sources. So we can have the same parameters, the lower and the upper limit of the recruitment age. Nevertheless, often our population results in a different distribution of age than the trial distribution. For example, the trial might still have a lower age distribution, and we have an older age distribution, although we have the same exclusion criteria applied. What to do about that? In prospectively planned calibration projects like RC Duplicate and like others, we can reduce the emulation gaps, for sure. We work hard to reduce the emulation gaps, but will it ever be zero? Probably not. It might be easier to calibrate pragmatic randomized controlled trials. There are not many out there. Most of the trials are highly controlled, and the emulation is therefore often more difficult. Let's talk a little bit about agreement measures. One is simply visual inspection, this example here by John Concato, where you see 5 research questions lined up here on the left side, and the black dots are the RCTs, and the open circles, the real-world evidence studies. And you see very nice overlap in most of the instances, but what you also see is substantial variation between the RCTs. Here, cholesterol levels and death due to trauma, quite some variation. And I bet you that's not because the trials are done the wrong way. These are probably studying slightly different study questions, so they don't emulate each other. They're not exactly the same trials. So that is important to note. Another agreement measure is simply correlation, where you have the scatter plot of the pairs, the real evidence RCT pairs plotted, and you estimate the correlation coefficient. This is work by Sean Forbes and Issa Dehabre, looking at 6 meta-analyses that are published and putting them all in the same 6 types of scatter plots here, and that is quite informative. Another way to do this is to look at the confidence interval overlap, and this is work by Jesse Franklin and others based on the data published by Hempkins and BMJ 2016. And what you see here is when you look at this middle column here, RCT versus real world evidence, when you look at the 95% confidence intervals, the expectation is that 98% of these real world evidence RCT pairs, the 95% confidence intervals would be overlapping. Right? And that's in fact reached 100% of the time. When you look at the 75% confidence interval, so the tighter confidence intervals now, we would expect that 84% would be overlapping of these pairs, and we see 81%. So we're well within the expectation, right? When you look from RCT to RCT, and even tighter 95, like the 50% confidence interval, you see that the expectation is that 63% are overlapping, and in fact it's 67%, 87%, and 100%. So you see variation here as well. So there's variation between RCT and real world evidence, but there is almost an equal amount between different RCTs. Again, that is likely because the RCTs are not emulating themselves very well, right, among the RCTs. And of course, you have variability between the real world evidence studies. And what becomes clear, and these numbers are all not robust and they're handpicked and all that, so don't put too much stock into the specific numbers, but what is clear is there's meaningful uncertainty to be expected across the entire evidence generation spectrum. So that is not limited to real world evidence alone. Another agreement measures would be kind of presenting multiple measures, recognizing that different stakeholders have different needs. You can do visualization, correlation, confidence interval overlap, standardized differences. You can have binary agreement measures like regulatory agreement that is p-value based, or estimate agreement that is confidence interval based. And you know, the stakeholders can pick the metrics that they want, but if we report all of them, we bring a more holistic picture forward. Now, if you think about all these issues, you can really summarize this in this figure here, where on the x-axis you have an increasing attention to study quality and the emulation success, how well the study emulated the RCT that you compare against, and how high the data quality is, how high the analytic the design implementation was, right? And that should correlate then with the expected agreement. And what we see is in these retrospective emulations, that it means that people did literature searches and find published real evidence studies and published trials that are, you know, roughly on the same topic area, and overlap them and see, you know, how overlapping are they. This is really putting kind of the lower boundary on the expected agreement, and you see kind of these correlation plots that I showed you already on Concado. Concado did some quality requirements, so I moved them a little bit higher, but it's quite subjective what I'm doing here. Then there are the bunch of targeted emulations where investigators set out specifically to emulate a bunch of RCTs, and they tried hard to apply the same inclusion-exclusion criteria and things like that, the outcome measurements. And RC duplicate falls into this. Kerrigan's work on oncology falls into that. And then, of course, there is the Rolls-Royce of these things. It is these double randomized experiments. Shadish in 2008 has published that, where in the education space, I'm not aware of anything in medicine where you randomize patients into either contributing to a randomized trial or contributing to a real-world evidence study. And then you do the randomized trial and the real-world evidence study and compare, and Shadish showed that you get exactly the same finding. Now, speaking about RC duplicate very briefly, it is a very specific calibration exercise with a very specific learning objective. The first objective is by replicating 30 RCTs and predicting 7 RCTs, what we really want to learn is, had we replaced an RCT with a single real-world evidence study, would we have come to the same decision? That's a very specific question of a regulator, a very meaningful regulator, to play that scenario through. What would have happened had we replaced that RCT with a real-world evidence study? And secondarily, we developing a process, how to do this and how to interact with a regulator, and then also, of course, a more academic exercise. What are the factors contributing to the agreement? Which means in the process of going from the raw data to the statistical analysis, blind feasibility analysis, to the actual analysis, there comes this point where we have to put our cards on the table, where we say, look, this is our best bet to emulate the study, and we deposit the protocol, a very detailed protocol. We register this at clinicaltrials.gov and say, this is our primary analysis. This point estimate is our best bet. And we compare that then against the RCT. Here's an example from this project where we're predicting the outcome of the Carolina trial with regard to 3-point MACE. That was in December 2018. We predicted there's no difference between linagliptin and glimepiride with regard to 3-point MACE. And then in June 2019, that was confirmed when the Carolina trial was released to the public, 0.98 versus 0.91, and the 95s are substantially overlapping. Now, what are the take-home messages? These systematic calibration exercises where we calibrate real-world evidence against an RCT, assuming the RCT is the gold standard, is a step forward to understand when and how real-world evidence may provide causal interpretations of treatment effects. So it is a very good learning experience for all of us, and we all wish we had an abundance of these examples, but it is hard work to do these studies. We learn about specific challenges when doing these exercises and how to come to valid study designs. And a lot plays out in the data quality of the underlying data that we're using. We learn more about the challenges in these large-scale emulation projects. They are substantial. We think that the emulation of most RCTs is tricky, particularly because most RCTs are really done for regulatory submission, certainly in the RC duplicate project, and therefore are often highly controlled, often against placebo. And these are all factors that makes it difficult to emulate well. I mentioned already that pragmatic RCTs are easier to emulate, but there are not that many out there. So also we don't really know how closely we did emulate. Our emulation success is not really quantifiable and therefore not correctable at the end. And then, of course, the question is the RCT that we're emulating against really the true treatment effect that we would expect? And that is a question that we also cannot really answer. And then, of course, the more fundamental question is, how many calibrations do we need to do in order to be satisfied? Do we need to do a bunch of calibration exercises in each therapeutic area, and how do we want to go about that? I think it's too early to come to a clear strategy there, but clearly we have to think about that. To some extent, what I'm concluding for this is often more about the data and the underlying data that we work with than the specific statistics. We have made a lot of progress with understanding study designs and how to do this the right way and what to avoid. The statistical methods have matured quite a bit. So what is a problem often is the granularity of the data, the completeness of the data that we're working with. It makes it hard to really emulate randomized controlled trials. And that is something that, I think the entire community is working hard on. With that, I conclude and hand back. Thank you.